Hello students, welcome to the third session of the chapter Electric Charge and Field. Let us look into the contents of the chapter. As you already know, we have discussed Introduction to Electric Charge, Coulomb's law in electrostatics. Today let us take up the third topic, that is electric field. And the contents to be discussed under electric field are about electric field and electric field intensity, that is definition and its explanation. Next, due to a single isolated point charge, I will be explaining about electric field. It is a simple derivation for about 2 to 3 mark. Next, when you have multiple charge system, how do you find total electric field? Comes under superposition law. And then a very important question, that is electric field lines and its properties. At last, pictorial representation of electric fields has to be understood. So let us take up definition and explanation of electric field and electric field intensity. For that you have to first understand what do you mean by electric field. See, I have already introduced you to first quantity, that is electric charge, and then second one electric force, and today I am taking up electric field, which is the third important quantity. It is also a vector quantity just like electric force. Now what is this electric field? See, you know an electric charge, if it is present around it, always it has some effect. How do we test that effect of that electric charge? For that you have to bring another charge and keep close to it. That means in that region around that electric charge, if you keep another charge, you will see there will be an electrostatic force of attraction or repulsion depending on what is that charge which is producing electric field and what is that charge which you are bringing in the region of electric field. So for the meaning electric field, you can refer this. Electric field is the space around a charge. It is the region or space around a charge in which any other charge, if you keep, experiences an electrostatic force. See, there are two charges here I am mentioning. One is source charge and the other one is test charge. Here it is mentioned, you can make out. See, the charge capital Q, if you are denoting, it is called as source charge, and Q naught, it is a small test charge which is also a unit positive test charge. See, what is this difference between capital Q and Q naught? See, capital Q is the one which is giving the effect of electric field around it, and Q naught is the one which is examining or testing the effect of the electric field of source charge. You can understand something like this. Capital Q is like a big rock and small q naught is like a small stone. And even this source charge can be a single charge or a group of discrete charges or any continuous distribution of charge. That means it can be a single charge with a large magnitude, or it can be a group of discrete charges. Discrete in the sense you can count how many total number of charges, or any continuous means you cannot count. There will be lot of charges spread and they are very close to each other. So all these things can be considered as source charge, and if you want to test the presence of electric field around it, you have to bring, as I have already told you, a small charge which is called a test charge, and it is always taken unit positive test charge for reference purpose. Now next question arises, how do we measure it or how do we write mathematically? See, for that here is the important definition, and it is called under electric field intensity. So what is the intensity of that electric field around that charge comes under electric field intensity definition. The electric field intensity at a point due to a source charge is defined as force experienced per unit positive test charge placed at that point without disturbing the source charge. See, if at all you want to measure electric field intensity, you have to calculate force experienced by that positive test charge unit positive test charge. So electric field intensity is electric force or electrostatic force experienced by that unit positive test charge is what is actually the mathematical formula of electric field intensity. See, as you know, in physics, we need to understand as well as put those things in mathematical form, and that is why electric field you have understood, which is the region or space around the charge which gives its effect. How do you measure it mathematically? It is with this expression. See, also one more thing you must realize, here if you get by chance a doubt like, uh, will not the test charge influence the source charge? Why only source charge will show its effect? Why not test charge? You must realize one thing here. Whatever source charge which we have, due to which we are finding electric field, is only influences the test charge, and the test charge will not influence the source charge. Due to test charge, don't expect the source charge itself experiences repulsion and it moves away, or experiences attraction and it comes close to test charge. That is why I told you source charge is something like a big rock and test charge is like a small stone. Test charge only will come under the influence of source charge. And its definition, mathematical formula, here you can make out E equals to, this is one mathematical tool, I'll tell you its purpose. It can be read as limit q naught tends to 0 f by q naught. So these terms are written in vector form. You can see here vector E equals to limit of q naught tends to 0 vector f divided by q naught. See, what is this q naught tending to 0? So limit is applied to test charge. See, it can be taken till close to 0 but not exactly 0. So it can be a very small charge whose value is very close to 0 but not exactly 0. That is the meaning of telling it is a small test charge. So I hope you have understood limit of q naught tends to 0 in the sense q naught will be very small but not 0. There will be a presence of a little test charge whose magnitude is very less. So thus you have to keep one thing in mind, electric field is measured by the ratio of force to the test charge. See, now let us try to write the explanation of the terms involved in the expression. As you already know from the definition itself, but still you have to mention the explanation of the terms. Here is, if E is the electric field intensity at any point, then F equals to force experienced by the test charge Q naught. See, it is always necessary in physics to know the quantities SI unit and dimension formula. So that is, if any time you learn a new physical quantity in physics, you must learn its SI unit as well as its dimension formula. The SI unit of electric field is Newton per Coulomb. See, here only I can tell you E equals to F by Q. This is the formula. For F it is Newton, for Q it is Coulomb. So the SI unit becomes Newton per Coulomb. And dimension formula, as you know, for force it is mLT minus 2 divided by Q. I have taught you in the previous session, Q is not the fundamental quantity. You have to use current which has Q in it. So current equals to Q by T, Q equals to I into T. For current it is A, that is the first letter of the unit, ampere. And for time it is T. So what you can write its dimension formula after simplifying is M1 L1 T minus 3 A minus 1. And now as you know already, electric field is vector quantity along with its magnitude. See which one will give you the magnitude of field. It is F divided by Q. Then you must show the direction also because it is vector quantity. In the formula you can make out F is only the vector quantity and Q it is a scalar quantity. So now electric field takes the direction similar to F. So wherever is F directing, that is only the direction of electric field. Thus you can write electric field direction is same as that of electric force. That is what here I have mentioned. And here is a note about positive point charge and negative point charge. For positive source charge, electric field will be directed radially outwards. from the charge. On the other hand, if you take a source charge to be negative, the electric field vector at each point points radially inwards. See, this you will understand in the next slides when I teach you about electric field lines. See, what we have learnt in this electric slide is, see, suppose if you have a charge Q, this one is a capital Q, that is source charge. Around it, it has its effect, that is only we call it as electric field. And to measure that electric field, we have a term electric field intensity. At any point you can just bring here, suppose here if you bring a small test charge, you can mention it this as Q or Q naught, then it will experience electrostatic force of attraction or electrostatic force of repulsion, indicating in this region there exists electric field intensity due to the source charge capital Q, and it is mathematically calculated as F by Q. It is a vector quantity. Electric field around this charge is a vector quantity. It has direction, and that is what here we try to tell. If it is plus Q, say if it is plus Q, the electric field lines that you will be knowing very soon will go out in this direction. Suppose if it is minus Q, then it will actually points inwards. So that I will explain very soon, but this much if you understand in this topic, more than enough. And always remember it's SI unit and dimension formula. See, now let us take up electric field due to an isolated point charge, which can be a 2 mark or 3 mark derivation, a small derivation. See, for this we have to consider a coordinate system. At the origin, I have taken a charge plus Q, and at a distance R, another charge Q naught, which is a test charge, is kept, and it is experiencing force as I've showed here. Now, as you have already learnt, whenever there are two charges separated by small distance, there exists electrostatic force explained by Coulomb's law. According to Coulomb's law, force on the test charge Q naught here due to charge Q, that is on Q naught due to charge plus Q, is written according to Coulomb's law, what you have learned from your previous sessions. F equals to 1 by 4 pi epsilon naught Q naught divided by R square into R cap. Here we are considering both magnitude and direction, hence we have written R cap. And also just now you learned that electric field definition is F by Q naught, force per unit charge. Here you can ignore limit. Only while writing the definition of electric field you can consider that, but for solving for some other derivation you can just write F by Q naught. Now F from the Coulomb's law, you can write this expression here, and then what happens, in place of F, 1 by 4 pi epsilon naught Q naught by R square into R cap, and this Q naught in the denominator remains as it is. Now you can cancel Q naught and Q naught, and you are left with the expression 1 by 4 pi epsilon naught Q by R square into R cap. That is the electric field expression in vector form, both magnitude and direction wise. And here in place of R cap you can make out one thing. We have written its formula. You know that R cap is vector R divided by magnitude of R. See, here in note I have tried to show you. You can recall from your first PU vectors topic. Unit vector R cap is given by vector R divided by its magnitude. That is what actually we here I have substituted, and we end up getting expression as 1 by 4 pi epsilon naught Q by R cube, because this R square and that R gets multiplied, and in the numerator you have R vector, and this is also one more form of expression for field. But mostly if you remember this 1 by 4 pi epsilon naught Q by R square into R cap, it is enough, and this is, as I told you, including magnitude and direction. See, in the next slide Here is only the magnitude expression for electric field. Suppose in numericals it is asked to find electric field due to this charge Q, given some value at a distance of r or some other value. You can directly substitute and find what is the magnitude of E. Here in note I have mentioned what is R actually, because earlier nowhere I have mentioned, that is the reason. So now R is the distance between source charge and the observation point P. And here also the same note for the purpose of using in place of R cap. Now this is all about the 2 to 3 mark derivation, electric field due to isolated point charge. Now let us discuss on superposition law for electric field due to system of charges, a topic very much similar to what we have learnt in the previous session about force, that is same as superposition law for electric force due to system of charges. Here we are discussing that on electric field. See, here also same thing. If you have many charges like number of point charges Q1, Q2, Q3 etc., then electric field at some observation point P due to the ith point charge is given by electric field E equals to EI, that is for ith charge we are in general considering Fi divided by Q naught. That means we are choosing any one charge as ith charge because we want to apply summation at the end, which will give us in a simpler way of understanding using mathematical tool, that is summation. So EI equals to Fi by Q naught, and you know Fi is from Coulomb's law 1 by 4 pi epsilon naught Qi Q naught by Ri square into Ri cap divided by Q naught as it is. So now what happens is Q naught gets cancelled and you end up getting EI vector equals to 1 by 4 pi epsilon naught Qi by Ri square into Ri cap. If E is the electric field at a point P due to system of charges, then by principle of superposition, electric field, here you make it as PLE, it is typed wrongly. Principle of superposition of electric field says it is total electric field E equals to E1 plus E2 plus E3 plus etc. up to En. And it is mathematically simple way written as summation I equals to 1 to n of EI vector. That is, using equation 1 we can write vector E equals to summation of I equals to 1 to n, that is charge 1 to nth charge, in place of EI 1 by 4 pi epsilon naught Qi divided by Ri square into Ri cap. So 1 by 4 pi epsilon naught is always constant, that is why summation is applicable only to Qi, where you can write it as Q1, Q2, Q3 etc. when you are adding, and similarly distances R1, R2 etc. Ri square into Ri cap. This is law of superposition, and the one big difference you can make out is there was actually two charges. Force, when it comes electric force superposition law, there were two charges, and here for superposition law of electric field there is only one charge. And here also you can state the statement of superposition law, that is every charge in space creates its own electric field at point independent of the presence of other charges in that medium, and the total electric field or resultant electric field is the vector sum of electric fields due to individual charges. That means you have to calculate individually and then you have to sum all of them, then you will get the total electric field of the entire system. This is all about superposition law for electric field. I hope you have understood all the properties. Let us discuss an important topic of the concept electric field, that is electric field lines and its properties. Now, what is this electric field lines? Actually, this is the pictorial representation to understand the electric field around the charge. I will tell you what exactly it is. See, Michael Faraday, a famous physicist, introduced the concept of lines of force. You can even call electric field lines as lines of force to visualize the nature of electric field. That is to understand how exactly electric field is seen. A small positive charge placed in an electric field experiences a force in a definite direction, and if it is free to move, it will start moving in that direction. The path along which this charge would move will be a line of force. So, what do you mean by this definition? Just show you by drawing a simple diagram. See, if there is an electric field due to some charge Q, capital Q, that is source charge, and if you keep a charge or an electron which is free in this region, it should be a small test charge. If you keep it here in this region, so what happens, if it is free, it will move, or it tends to move. It can move in this direction or it can move in this direction, that is either inwards or it can be outwards. It depends on what is the nature of the source charge and the nature of this test charge which we have brought in the region of electric field. This path along which the charge moves is actually called as electric field line. This is only, I meant to tell, the visualization of electric field. It can be straight line or it can be curve. If it is a straight line, it is very clear electric field is represented by field line in straight line. If it is a curve like this, then you need to draw the tangent and you have to represent the direction of electric field along the tangent. See, where we get this curve line, I'll show you in the next slides. So for time's sake, now you have to understand electric field line is the path along which a unit positive charge moves or tends to move in an electric field. Or electric field line is a curve whose tangent at any point gives the direction of electric field at the point. This is what is exactly mean by electric field line. Now to understand it further, let us discuss properties of electric field lines. First property, electric field lines start from positive charges and end at negative charges. If there is a single charge, they may start or end at infinity. Now if at all you want to understand this, I have to show you the pictorial representation which I have drawn in this slide. See here, if it is a point charge, see this is a point charge which is positive, because here I have mentioned Q greater than 0, or here only you can mention plus, and this is minus Q less than 0, and these both are point charge. So that means in 3 dimension you can imagine all these lines drawn in all directions, but this is a sheet, a plane, so I can draw only 2-dimensional diagram. But since it is a point charge, it has lines in all possible direction in space. So see here, this is positive charge. Now all the field lines from the positive charge around it moving away from the positive charge. The direction you can make out from the arrow, and you have to put the arrows going out from the positive charge. This is the electric field lines how we draw for positive charge, point charge. Similarly for negative point charge, it is all the lines which are terminating into the charge. That means it is getting inside towards the negative charge. This is the representation for point negative charge. And if it is single charge, see here I have represented the single charge. So now you can see the lines are moving towards infinity, and here as if the lines are coming from infinity. That is the meaning what I have shown in the bracket. Second property, in a charge-free region, electric field lines are continuous curves without any breaks. That means electric field lines, once when we start drawing, you don't get any breaks. It is a smooth curve. So here I can show you in the next picture. See here, these curves nowhere you can find. Once I start, it is continuously drawn. So you can tell the electric field lines are continuous curve. Even here you can find till here it has its effect. So we have drawn. So nowhere it is discontinuous. Third property, two field lines can never cross each other. Here justification also we have given, if it is asked for 2 marks, why two electric field lines can never intersect. You can write this, that is if they did so, if it is true, this property is true, the electric field at that point of intersection will have two directions, which is not possible. That means if you consider two electric field lines, assume there are two electric field lines like this, which are directed in this direction. Now if you keep a charge at the point of intersection like this, this charge now has two possibilities. It can move here also or it can move here also, but keep it in mind, at one point of time this charge has to move only in one direction. At the same time it cannot has two directions to move. That is the meaning of this property. Two field lines can never cross each other. If they do so, they have two directions, which is not possible. At one point of time electron can move only one direction. To explain this, we have to write the electric field at the point of intersection will have two direction, which is not possible. Okay, that is about third property. And next is electric field lines do not form any closed loops. This I can take you to the same slide where I have drawn here. See, here we have taken two like charges, positive and positive. Nowhere you are able to see two electric field lines are crossing. And why this pictorial representation is like this, I'll explain in the next property very soon. And here also in this diagram you can make out, nowhere you can see forming any loop. See here, starts from positive, ends to negative, even downwards starts from positive and ends to negative. So in any of the diagram, wherever you draw electric field lines, you never see forming closed loops. This is the fourth property, important property. It can also appear for 2 marks. This is based on conservation of nature of electric field. Fifth property, the electric field lines possess longitudinal tension, that is they tend to contract longitudinally or lengthwise. This explains attraction between unlike charges. What do you mean by this? For this we have to take up this diagram. See, there are two charges which are unlike, one is positive and another one is negative, and you can see here the lines from positive, as you know, emerges out and they terminate to negative. So these lines will find a negative charge very close to positive. What happens? All the electric field lines start terminating to negative charge, and this is even downwards also same thing. See, upwards and downwards both, it is starting from positive and terminating to negative. So that means it is contracting lengthwise, longitudinal contraction you can see, indicating the contraction is for unlike charges, that is plus and minus. And here why there is no electric field line, that is because the effect is now decreased. So till it can go here, and around charge to some extent electric field will be present. After some point it won't be there. So that is why we are unable to draw the lines here. But definitely you can show from here the field line goes and it will try to contract towards negative charge, and here it will try to terminate into negative charge. This is the meaning of longitudinal contraction. And now next property is almost like that, that is exert lateral pressure on one another, they tend to repel each other. This explains repulsion between like charges. Meaning is, in this diagram two like charges you have plus and plus, and here you can see plus and plus like charges cannot come close to each other due to the electrostatic force of repulsion, and hence when you draw lines, those two lines can never meet, as we have learnt already in previous properties. And what it does here is, This electric field line exert pressure on this and this will exert pressure on this. So lateral pressure, what happens, they cannot come close to each other, indicating these two charges must be like charges exhibiting property of electrostatic force of repulsion. Next property, an important property, electric field lines are always perpendicular to the surface of charged conductor. Meaning, see, whenever you see electric charges on any shaped body, suppose if I consider sphere, if you want to show how exactly electric field around it, then you have to draw exactly electric field line perpendicular to the area from where you have started the electric field line. Reason, if the lines of force are not normal to the conductor, the component of electric field E vector parallel to the surface would cause the electrons to move and would set up a current on the surface, but no current flows in the equilibrium condition. So that means you can understand in this way. See, if there is a spherical conductor on which we have charges spread like this, see everywhere charges on the excess charges present like this. So if you want to show through electric field lines, that is visualization of electric field line, you have to draw exactly perpendicular to that unit area. So that is, it has to be straight line like this, writing an arrow. Or here if you want to show anywhere, it has to be exactly a straight line with an arrow indicating. So that means electric field lines on any surface must be drawn exactly perpendicular to that particular region. Suppose if it is not a straight line, if it is a line like this, not perpendicular line, so what will happen? As you know, in vector analysis, if the line is vector is not on x-axis, not on y-axis, you can resolve this into two components, that is one along x-axis and one along y-axis. So what happens if you draw one along x-axis and one more along y-axis, and then you will find now two direction, and this is, of course, this is perpendicular, and electric charges cannot fly out of the sphere. That means it has to stay here only, because we are talking about charges at rest in this chapter, electrostatic charge and field. And if you think the charge will move in this direction, then what happens here also, the charge will experience definitely force, because you know electric field equals to F by Q. So F equals to Q into E. So any charge placed in electric field definitely experiences force, and if you think it can move, it has path here, it can move in this direction. That is what I try to explain. Then it produces current, but current is not produced under equilibrium condition, because here all it is at same potential. Anyway, in next chapter I can tell you about potential, but right now you understand the chapter is about electrostatic field and charge, that is charges cannot move, it has to be there only. That is the meaning of this property, electric field lines are always perpendicular to the surface of charged conductor. So the left out line is this line only, and here definitely leaving the surface the charge cannot move. So you can have the option of drawing electric field line like this. Next property, again it is one of the important property to understand many concepts of the chapter. Electric field lines do not exist inside the conductor, because this I can tell you, if you have, say I'll show you here, if you have a sphere on which inside which there are equal number of positive and negative charges, because this is a this is a conductor and it possesses equal number of positive and negative charges. Suppose if you apply electric field from outside, that is this is negative side, assume this is positive side. Then you know already from properties, field line starts from positive side and end to negative. See, like this is negative side and this is the arrow. Due to this electric field, inside the sphere also conductor there exists internal electric field. See here, charges are separated because close to negative charge all the positive charges of the conductor come and accumulate, and due to this positive charge all the negative charges redistribute close to this positive, and due to which there is separation of positive and negative charge. And as you know, wherever there are positive and negative charges separated by some distance, there exists electric field. See here, there exists electric field which you can compare to outside. This is moving towards this direction and outside is towards this direction. Electric field is vector, so definitely they cancel out each other. So electric field cannot exist inside the conductor. You can understand by this way also, or else one more simpler way you can make out. Inside the conductor you try to keep more number of excess charges which are like charges. What happens, due to electrostatic repulsion they move from each other and they will accumulate on the surface of conductor at particular distances where they will not undergo any electrostatic force of repulsion. This way also you can understand this last property. And here is one important point. Sorry, I'll show here, which you have to analyze. The magnitude of the field is represented by the density of the field lines. That means if the lines are very close to each other, if the lines are very close to each other like this, assume these are electric field lines parallel to each other, you must realize. If lines are close to each other, then you should assume electric field is very strong in this region. If the lines are far apart like this, you should assume electric field is very weak in this region. That is the meaning of this point. And even this can be a property you can include as the last property as well. That's why I am mentioning here. So these are the properties of field lines. For 5 mark, at least 5 you have to remember. I hope you have understood all the properties. Now the last topic is pictorial representation of electric field lines. See, while explaining properties of field lines, I have tried to explain the pictorial representation. The first two diagrams is about positive point charge and negative point charge. And this is for like charges. Drawing electric field lines, you have to show all these lines like curve, and here is the direction in which due to repulsion charges can move away from each other. And but these lines you have to draw curves only, showing lateral pressure. Next comes unlike charges, and you have to show longitudinal contraction, and here also this has to be curve, like it is coming and meeting towards negative charge, and its effect is still here, so that is why you can stop at this point. This is about pictorial representation, you can expect for 1 mark each. Now this is all about the topic electric field and electric field line. Now before I end the session, I again would like to leave you guys with the questions, important questions. Here are few questions. If you are thorough with this, it's enough for the topic. First one, what is electric field? Write its formula. Then SI unit and dimension formula you have to learn. A small derivation as I have showed you, that is for 3 mark. Electric field due to isolated point charge. Superposition law for electric field, 2 mark. Electric field lines and lines of force meaning you have to learn for 1 mark. It is pictorial representation. It is an imaginary line. Keep it in mind. Electric field lines are imaginary line. It will not exist really. but the effect of electric field is real, but electric field lines are imaginary. That is for 1 mark. Write the properties of field line. 5, as I told you, you have to remember for 5 mark. Then pictorial representation, and at last this property can be asked for 2 mark. Electric field lines, why they don't intersect, explain, for 2 mark. Thank you one and all for watching.